Today's notes are on polynomial functions. This is section 2-2 in your textbook. Now, polynomial function is a fancy word for something that we've been working with for a long time here. And this is an example of a polynomial function. And you might say, my goodness, this looks terrible. But really all this is, all these a's stand for different coefficients of a function. And then x to the nth is x to some power. So an example of a polynomial function would be f of x equals, let's just say 5x to the fourth plus 3x cubed plus, let's just say 0x squared, and let's say minus 2x plus 7. So there's an example of a polynomial function. Now, you have dealt with linear functions quite a bit in your Algebra 1 days. You've dealt with functions with x squared quite a bit in your Algebra 2 days. We're dealing with any value for n here, any degree, any power. So what we want to know is what the graph of this would look like. Would the graph kind of go up and down a little bit? Would it do something like this? What does this graph look like? So that's the first thing we need to talk about, and it has to do with this number in front here and this greatest power or this degree of the function. So let's figure out what these graphs would look like. Now, there's something called the leading coefficient test. So if n is odd, so this is a function like y equals x to the fifth plus something. All that matters is its greatest power. If n is odd, the greatest power is odd, your function will always have this kind of shape. It'll start in the lower left-hand corner, come up here, do something in the middle, who knows what, and then end up in the upper right-hand corner. Now you have to be careful because I said it always does that, but if you have a function where the leading coefficient is negative, let's say, it'll flip that entire graph. So it'll look something like this. Okay, if your leading coefficient is even, so like if you have something like y equals x to the fourth plus something, 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 doesn't matter what comes next. All that matters is your greatest power is an even number. Well, in that case, your graph will always look something like this. It'll start in the upper left-hand corner, come down, do something in the middle, and end up in the upper right-hand corner. Now, again, if that term happens to be some negative value, we know that will flip our graph, so we know it's going to take that whole thing and turn it around like so. So basically, from looking at your leading coefficient, you can tell the general shape of your graph. So that's what we want to do in this first example. First example says describe the right and left behavior of the graphs. So basically, I want to know what's the general shape of each of these graphs. Okay, let's take a look at this first function. This first function, since the first term, and we don't have to look at any of the x terms or any constants, all we have to look at is the term with the greatest power. Since that term with the greatest power is positive, okay, and it is odd, our graph will look something like this. We don't know exactly what it'll do in the middle, so the stuff in the middle is unknown. We don't know about this stuff here, but we do know that it'll start in the lower left corner and end in the upper right corner. Second one, leading coefficient is even and it's positive, so we know this graph's going to have a shape that starts in the upper left corner. Who knows what it's going to do in here and end in the upper right corner. Third graph. Okay, our leading coefficient is an odd power. It's also negative, so just being odd will look something like this first one. But since that first term's negative, it's going to actually come downward now, do something in the middle, who knows what, and end up in the lower right corner. All right, fourth one here. Real common mistake with this fourth one. I put this on here to try to trick you. You see the mistakes some people would make? Now, when I say leading coefficient, do not just go with it as it's written. It's got to be the greatest power. So think of this as negative x to the fifth plus 2x to the fourth. Greatest power is odd, not that x to the fourth. That doesn't influence the general shape of the graph. It'll influence the stuff in the middle, but not the general shape. So in this case, greatest power is odd. It is a negative leading coefficient, so it's going to look something like this. Okay, so based on the greatest power, whether it's even and odd, whether it's positive or negative, you can tell the general shape of any polynomial function. Okay, now that we've got that taken care of, now that we know the general shape, how do we know what's going on in the middle? Where is this thing going up and down? Where is it going through the x-axis and the y-axis? That's what we want to focus on. So this second example here, find the zeros of the function and sketch a graph. Well, we know in general this function is going to start in the lower left corner, do something in the middle, who knows what, and end in the upper right corner. We need to be a little more specific than that. So what we would really like to know is where does this graph go through this x-intercept? Where does it go through the y-axis? Where's the y-intercept? Here's how we find that. Well, we know to find x-intercepts, if we plug 0 in place of y and solve for x, we will find our x-intercepts. Now, we can't really see what they are right now, so what we have to do is try to factor this expression here. So I'm going to say 0 equals. Now, first thing we do when we factor, look for something we can pull out of every term. Every term has an x, so I'm going to pull that out. So x times x squared plus x minus 6. All right, now we need to remind ourselves of our factoring skills. So we say 0 equals, don't forget the x. We know if this can be factored, it'll factor like two binomials. X times x equals x squared. And I need two numbers that are going to, let's see here, add to this term here, this 1, multiply to this term here, negative 6. So what adds to 1 multiplies to negative 6? Okay, negative 2 and 3. Now that it's factored, finding these zeros, finding these x-intercepts is actually relatively easy to do. Because if I plug 0 in place of this x right here, the whole thing would equal 0. So there's one of them. If I plug 2 into this term right here, the whole thing would equal 0. Or if I plug negative 3 into this term here, the whole thing would equal 0. So these are the x-intercepts. So we can either write them as intercepts. Remember, if I plug 0 in, I get a y value of 0. If I plug 2 in, I get a y value of 0. Or if we plug negative 3 in, we get a y value of 0. Sometimes when we're just talking zeros, we can write them in this format. Let's say we could either plug 0, 2, or negative 3 into this function. So now our graph can be a little more specific. We can say, hey, if x equals 0, so that's this point here. If x equals 2, that's this point. Or if x equals negative 3, that's this point. Y equals 0. So there's 3 points in our graph. Our y-intercept, if we plug 0 in place of x, we get 0. So this is your y-intercept as well. So your general shape of the graph is going to come up from the lower left corner, come down here. Let me try to hit that point. There we go. And end in that upper right-hand corner. And there's going to be your general shape. Now, it can get more specific and find specific points in here. We'll talk about doing that later on. But for now, we're finding these x-intercepts. We're finding these zeros, which is aiding us in graphing this function. Okay, let's try another one just like that. Same exact directions. In fact, because of this x cubed, you know it's the same general shape. So I'm just going to do this to remind myself that's what my graph's going to look like. We need to factor. So I'm going to say 0 equals, I know I can pull an x out of every term. And I'm going to go through this relatively quickly because it really is the same kind of logic as the previous problem. So we have our x-intercepts, which we can write as points, or we can write as the x-intercepts in a bracket. So going to a more specific graph, we know that this graph is going to go through the x-axis at 0, at negative 2, and at negative 5. There's your y-intercept as well, so I'm going to bring this sketch up. We'll go through those points, and there it is. Okay, so let's take a look at a little different kind of problem. So now we know how to find the zeros, how to sketch a general graph. What if we have to go the other way? What if we know the zeros and we need to come up with the function? Let's just think, I'm going to go back and look at the last problem. If you start with your zeros can we somehow go backwards and come up with the function? Let's think about this. Here's your 3 zeros. 3 zeros came from our 3 factors. Our 3 factors we got from this function. So if we can write our zeros as factors, then instead of factoring, multiply them together, we can come up with our function. I think that's something we can do. So if you know the zeros to start, let's write our function. We can say f of x equals. And let's write these as factors. So we can say it's going to be x plus 4 times x minus 2 times x minus 5. And remember, if negative 4 is a 0, that means we can plug it in to make this function equal 0. So that's why x plus 4 was a factor. At this point, we need to multiply. It doesn't matter what order you multiply in, but do not try to multiply all these together at once. Sometimes people try to take shortcuts. Don't do it. Pick 2 of these binomials, multiply them together. So I'm going to pick these first 2. And if I multiply those, we will get x squared plus 4x minus 2x. So I'll write that as plus 2x minus 8. And then we need to multiply that by this other factor, x minus 5. So again, it's following the distributive property, multiplying every term of the first by every term of the second, which will give us x cubed minus 5x squared plus 2x squared minus 10x minus 8x plus 40. So let me combine some like terms, clean this up, write this as a function. So my function is f of x equals x cubed minus 3x squared minus 18x plus 40. And we really should have f of x or y equals at the start of this, just so that it is a function. Okay, one last idea I want to share with you, and here's this last problem. Sketch the graph of this function. Now, it's the same directions that we saw back here. Sketch this graph. We know the general shape is going to be something like this. What we did before is we factored our functions to try to find the zeros. However, if you look at this, there's no way to factor this. There's nothing you can pull out of every term. There's no way you can break this down. It's not factorable. So finding our zeros by factoring is a convenient way of doing this if the problem is factorable. If it's not factorable, we're kind of stuck. So what we have to do instead is just think of some other methods that we could use. And I'm just going to jump right to my graph here. I'm going to plot some points. I'm going to think, well, if x is 1, we get 1 plus 1 plus 1. Then we get a y value of 3. If x is 0, we get 0 plus 0 plus 1. We get a y value of 1. If x is negative 1, we get negative 1 plus positive 1 plus 1. We get a y value of 1. If x is negative 2, we get negative 8 plus 4 plus 1. We get negative 3. And we could keep going like this, but in general, we know our general shape of the graph. It's going to end up doing something kind of like this. And there's our graph. So sometimes we can't find those exact zeros by factoring. There's other methods we're going to learn about that'll help us find these exact zeros like here. But for now, if it can be factored, that's a convenient way to do it. If it can't, we're stuck. We just need to plot some individual points. Okay, we've got an assignment on page 112 to take a look at. Once you've completed this assignment, take a look at the next video. It'd be lesson 2-3.